There's a problem in the thermodynamics book by Singer, which is very interesting because it helps us really understand what happens in a problem, and it helps us to put aside common perceptions on different problems. The problem is number 359, as you said, and what it tells us is that it tells us there is a piston cylinder, okay, and initially it contains 1.4 kilograms of saturated liquid water at 200 degrees C. Now, heat is transferred to the water until the volume quadruples, and the cylinder contains saturated vapor only. Determine the volume of the cylinder, the final temperature and pressure, and the internal energy change of the water. A closer look at this problem tells us why it is different. Look, there's an initial condition, and for the initial condition, we have two properties, two um, intensive properties. First is temperature, is 200 degrees C, and the second, it is saturated liquid water. Therefore, X is 0. So we have two properties, and that's enough to read or calculate all other properties. The initial condition is perfectly known. Now, let's look at the final condition. At the final condition, we know that the volume has quadrupled, so we know the specific volume. We shall talk about it in detail later on, but that's what we know. The second point is that it is saturated vapor only. So we know two independent properties. One, saturated vapor, so X equals 1, and 2, the specific volume. But look at the picture. The picture, as it is drawn, and as usually we assume, for such a case, we assume constant pressure. But what the problem is telling us doesn't talk about constant pressure. And in fact, as we shall see, the pressure changes. And this configuration just is blind to the fact that if there is a spring above it, or there is friction, or there's anything else, it just tells us that there's a piston cylinder device. And from the problem, and from whatever the problem has told us, we have to understand if the assumption that the pressure remains constant in such a device, which is very common in many problems, is correct for this problem or not. Well, this is all our knowledge of the problem. Uh, Initial conditions, M equals 1.4 kilogram, X is 0, and T equals 200 degrees C. It is water, and at the final, V2 is 4 times V1, and X2 equals 1. So to start with the problem, we have to know water properties at the known condition. The known condition is T equals 200 degrees C, and for T equals 200 degrees C, there's a lot that we can read from the table. We know that Psat equals 50, 54.9 kilopascal. We know that Vf, a specific volume for saturated liquid, is 0.001157 cubic meters per kilogram. We know that Vg equals 0.12721 cubic meters per kilogram. And since the problem has asked us to calculate the energy difference and the change in internal energy, we would also read energy values from the same table, just the next few columns. So UF is 850.46 kilojoule per kilogram, and UFG equals 1743.7 kilojoules per kilogram, and UG equals 2594.2 kilojoule per kilogram. So now these are water properties at 200 degrees C and has little if anything to do with our problem. Now, it's a very good job to transfer this knowledge on a diagram and see what the diagram tells us. Well, if this is a TV diagram for water, then the temperature of interest for us is 200 degrees C. And well, let's assume that this is 200 degrees C. And so this is our constant pressure line, and this would be our constant temperature line. Is 200 degrees C. Saturation pressure, this line P equals 1554.9 kilopascal. And there are two points here that we should use. One is VF. Here VF equals 0.001157, and VG, which is here, is 0.VG equals 0.12721. These are the knowledge that we have found from the table. We could also write UF, which is U at this point, UG, U at this point. We could write it. I won't write it here, not to make my drawing noisy, but it's very interesting to learn what the properties here are and just to know what our positions as compared to a known position are. So here, critical point at T critical equals 373.95 degrees C. So I'll compare this 200 degrees C to this 373. And P critical, the pressure at critical point, is 22064 kilopascal. So this is 1554. This is 22064. Now, an interesting knowledge from the table is what's the specific volume at this point. And that is V critical equals 0.0031104. Look, this is 0.001157 and this is 0.003. So this is 3 times VF at 200 degrees C, about 3 times, and VG is far away. VG is 1. It means that it is almost 100 times far away from this point. This is almost 3. This is almost 100 times. So it's very far just to understand the scales of the graph that we are talking about. That's how it is. Now, what does the problem tell us? That's very interesting. The problem tells us that in the final case, V2 equals 4 times V1. Now, let's see what that means. I would select a system control, a boundary for our problem, which is, of course, the water inside this cylinder. I write down the mass conservation law for this boundary. Mass conservation tells us that dmCb divided by dt equals m dot I minus m dot E. And since nothing comes in and nothing goes out, then between initial and final condition, we learn that m2 minus m1 equals 0, or alternatively, write it as v2 over v2 minus v1 over v1 equals 0. And since v2 equals 4 times v1, therefore v2 should be 4 times v1. Our initial condition is here. This is point 1. This is point 1, and that's our initial condition. The problem tells us that our final condition, the volume, is 4 times initial volume, and we learned that a specific volume should be 4 times initial specific volume. So if we calculate V2, you see we know V1, V2 equals 4 times V1, and that equals 4 times 0.00115 and we learn that V2 equals 0.004628 cubic meters per kilogram. Now, let's transfer this knowledge over our graph. You see, this is point 1. For point 2, our specific volume is 0.00462. Our critical was 3, so this would be slightly to the right of our critical point, and this would be our point 2. So V2 equals 0.004628. You see, with these two conditions, that point 2 is saturated vapor and the specific volume is 4 times the initial specific volume, there is no way that the pressure can remain constant. And in fact, the process 1, 2 is a process in this way. This is process 1, 2, with a change in pressure, temperature, and specific volume. All are changing. Now, point 2 is a point where its specific volume is known. It is known that this specific volume is saturated vapor, and just with these two knowledge, we could just move to the tables and read what temperature and pressure for this specific volume and the saturated vapor are. And if we do this, which I have done it, P2 would equal 21, 22 to 3.5 kilopascal, and T2 would equal 370.7 degrees C. Just look, critical point is 373, and our point 2 is 370.7. So it's very, very close to the critical point, and it's just slightly to the right of the critical point. We could also read UG from the table, which is also U2, and that would be 2192.4 kilojoules per kilogram. And this is all the knowledge of point 2. Now, almost all the questions of the problem are answered. The only unanswered point is the change in energy. Well, the change of energy is delta U, and that equals mass times delta U. That means that U2 minus U1 equals M times U2 minus U1. And we'll have everything here. The mass, the problem has told us, is 1.4 kilograms. U2, we just calculated it, and it is 2192.4 minus U1, which we read it earlier on, 850.46, and the outcome U2 minus U1 would be 1878.7 kilojoule. Well, a process has happened. There are change of properties. We know two of the initial properties. We know two of the final properties. So we can calculate all properties, and we can know the property change, like change of internal energy. We could have also calculated the change in enthalpy, the change in entropy, since we can know this change. Now, how is this changing property related to the heat that is transferred to this system? That is what we shall learn in the first law of thermodynamics. Thanks for watching, and cheers.